All right. So, whoops, let's see what's happening here. Continue. So let me, oh, I can hear
More
them.
people are joining,
Yeah,
so maybe we can wait
yeah,
a couple minutes.
yeah, well, wait a minute. I can, every time somebody joins, I get a ringing in my ear.
Yes.
Robert,
Yeah?
this is Joan Bailey Wilson. I have
Oh.
a question.
Yes, Joan.
Did you guys decide, are you having the 4th day?
Yes, we are having it.
Okay.
I'm not sure how we're doing it, but we're having it. Okay.
Okay. All right, good. I signed up for it. I just want to make sure that I keep it on my calendar.
Yeah, and actually most people, I think nearly everybody signed up for it. So I've got to give it.
Yeah. Good. Excellent. Yay.
Yes.
And I'm so glad you all are recording this because I have summer interns coming this summer.
Oh, good.
And it is going to be so great for me to be able to have them watch this course.
Sure.
And, you know, I mean, we all have new people all the time, and it is going to be such a fabulous resource. I'm so delighted you guys are doing this.
Well, you know, thank you, Joan. It was Wayne State University, so a graduate student there who emailed me and said, would I do a virtual course? And I've decided I'll do it. But for all the difficulties that occurred, I saw you were there yesterday, last day. It was, and let me say this to those who are present. I hope my computer won't go down again. But if it does, just wait. I'll be back. I have no idea what it is. It's Google or something wants to count errors. Don't ask me why. I have no idea.
We all have been getting used to those kinds of interrupted things in our Zoom meetings. Your Wi-Fi cuts out and you just have to reconnect.
Yeah. Okay, so let me just say that, the other thing I want to say to those people, please do ask questions, everybody there, but please, like Joan, please let me see yourself as well as unmuting yourself. Keep yourself muted otherwise, but I love to have questions. I will try and answer them the best I can. Okay, so I think it's time to start, and we're doing this. This is very weird. I'll tell you. I have no control over the cursor, but Yunju has, and hopefully she'll be doing things the way it is. So, what we're going to do today now. Oh, I know what's wrong. I have to click on this other screen. There we go. No, now it's not doing anything. Oh, I see. I've got to do this. All right. So we're going to talk about exploring pedigree data. So what do we want to know about genetic data? Oh, I think, yeah, you will have to do all the clicking, apparently, Yunju. I'm sorry about that, because I don't know what's going on here. So first of all, there's the source of the data. How are they collected? What is the source of the pedigrees? You have to answer that. But then when you want to know is the types of families in the data, how big are the families? Are there sibling pairs or extended pedigrees? Are there the same number of males as females? Well, PEDINFO will answer that. If you're interested in the correlation of the trait within families, are sibs, spouses, or other relatives correlated? Are these correlations sex specific? F-core will answer that. And then you want to know something about the trait distribution and transmission. Does the underlying trait distribution suggest a genetic factor? Is the trait segregating in families? Well, S.A.G.E will answer that. So let us look at some example data. We're going to use as our data some schizophrenia dopamine beta hydroxylase data set. Dopamine beta hydroxylase, it catalyzes the conversion of dopamine to norepinephrine. And the data set comprises 123 Caucasian pedigrees. The families were ascertained for having 2 members with consensus diagnosis of schizophrenia, DSM-3R criteria. So the phenotypes that we have are affection status and age of onset for schizophrenia, dopamine beta hydroxylase and transformed dopamine beta hydroxylase levels, and 2 psychometric factor variables obtained from principal component analysis. We also have genotypes for over 5,000 autosomal SNP markers from the Illumina 4B panel. So here's what the data set looks like. And you can see there's on the first column is the family, or pedigree, if you like, whichever is called the family here, that first column. Next column is the individual. Then you have the father and mother of that individual, sex, which we here have labeled M and F, affection status, unaffected or affected. A dot indicates unknown, age at exam or age of onset. And then we have DBH level, and you can see on this slide, they're all unknown. And the square root of DBH, and then these 2 factors I talked about. Then you have a whole bunch of markers, and we'll talk about how you code the markers later on. So now we're going to look at summary statistics from PEDINFO. So the PEDINFO provides descriptive statistics on pedigree structure, first of all, including the means, variances, and tables of family, SIBSHIP, and pedigree sizes. It counts each type of relative pair. It also can provide statistics specific to individuals with non-missing values for traits and covariates. In other words, it can either talk about statistics about the pedigree structure or about specific individuals that are not missing for specific traits and or covariates.
So now, yeah.
Carry on, Yunju, carry on.
Yes. So now we'll look at the program a little bit deeper. To run the PEDINFO, there are 2 default input files for S.A.G.E, which is the pedigree file and the parameter files are needed. Then it generates the default, the INF file, which is the information file, and 1 or more analysis result file, depending on the analysis option that you have chosen. Just make sure, just like we said on the first day, always check your .inf file before you look at the analysis result file. In the example, we will actually look at the options, which is the affection status, the trait equals affection status, and then we will leave the all other options set to be just the default values. When you open the GUI, you actually see this. I think we actually showed how to actually generate this part. And when you have this job, you won't see this part, okay? But how you actually generate the PEDINFO job, okay? What you do is actually, you just drag whatever the program that you want to run, in this case, PEDINFO, drag and drop to here, then it will populate this tree structure. Okay, then as you can see, you see that it says it automatically generates default parameter file, but it's asking for the missing data file. So you have to actually put the data, proper data file that you want to use it. Okay, how you do that? You just drag your data file that you have internally, then just to drag and drop to here, right there. Then it is look like this. Now you have your parameter file and your pedigree file right there. So now you are ready to go to the next step, which is the analysis definition pane. So now in here, we wanted to actually specify our trait, which is the affections, right? So let's look at that part. You just click here and it will drop down every trait. It's in the data file. And then you just select affection right there. Okay. Then it's ready. So you click the run. Then it will pop up this window. So this analysis information window pops up to confirm the analysis option that you just specified, which is that specifying the name of the trait and the leaving out the rest of the option to be false by default. Okay. Then in here, I think you want to note like two different things. If you are running like a long job, but PEDINFO is relatively small, like a quick and simple program to run, so it won't take long. But let's say like other program, like a linkage or other program that takes a long time, what you can do is actually you can generate the parameter file in this way and then use this parameter file and then to the run job on Linux like that. Okay. And also another thing that you want to make a note is that if you want to make some modification in this part, let's say, oh, I changed my mind and I want like each pedigree to be printed out, then you can click right here to make it just false, the true, sorry. So type it true, then just okay. Then it will actually change the option that you did in the previous step, but just to confirming that you changed it. So two things you want to make sure. Okay. And when all option looks good, now just click OK right here. Okay. And also another way to see your parameter file is just clicking, double clicking this part. Okay. So that's how you can just see your parameter file as well. Now, then it automatically pops up this task window showing the job or the program that you are running, the status of the program that you are running. When it says right here, finish it, okay, that means the pedigree is done. It is done running the pedigree. Okay, now you are ready to actually look at the output file it generated. Okay, Dr. Aston will explain how the PEDINFO output looks like.
All right. So if you look at this output, it says general statistics, all pedigrees. And you can see on that the pedigrees are defined by having the same pedigree ID. If two people have the same pedigree ID, then they are, as far as the program is concerned, they are all part of the same pedigree. However, look at this bit here, and it says although there were 123 pedigrees, there are 124 constituent pedigrees. What this is saying is, among those 123 pedigrees, there are in fact two lots of people with the same pedigree ID, but they're not connected in any way. So we call those constituent pedigrees. That often happens, and they will be analyzed as though they are independent. Because there's no way the program can identify how they're connected. Now we're going to look at all pedigrees and look at the trait affection. So this will be all those individuals who have that particular trait affection. And you can see in this, there is a bit that's highlighted that talks about concordant unaffected pairs, discordant pairs, and concordant affected pairs. If you have a non-binary phenotype, that won't be output, of course. So the pedigree info program, let's consider now the options. We're going to look at the trait DBH. We're going to say we want the individual pedigrees to come out, not just the total. And we want the output for only trait relevant statistics. No, we don't want it. We're going to say that's false. And the output then will look like this. We'll see, first of all, a particular pedigree coming out. This pedigree, it tells you how many SIB-ships there are. I want to get this, excuse me a minute. It will tell you the constituent pedigrees. There's one in this particular data set, and it will give you information. This one says in this particular case there are no marriage rings and no loops. We'll talk more about that in a minute. It tells you how many, for this particular pedigree, how many male and how many females there are, and so on. And the pairs, the number of pairs in this pedigree. Excuse me. I forgot to turn the phone down. All right. So let's see. This trait, this tells you that we're going to look at each individual family for family members without missing values for the trait DBH. And you can see again all the various statistics. For this particular pedigree, you've got the number of pairs of the different types and so on, and the number of individuals, mean and maximum, and the count. Let's look at all pedigrees. It tells you for the same for all pedigrees together. And you can see on this particular slide, you can see that there is, again, one pedigree, 123 pedigrees, but there are 124 constituent pedigrees. And now you see here, this is, it talks about the size of the inheritance vector, which is, we're going to talk about later. But what you want to know for now, it's telling us that between 0 and 2 pedigrees have 28 of these bits. But 3 and 4 pedigrees have 24, right down to 17 to 32 pedigrees have 9. Now, all you need to worry about at this stage, we'll talk about it later, is that if it's more than about 20, you may have to cut the pedigrees for linkage analysis. However, it depends on the computer you have access to. With the one that we have access to, we've been able to go up to 28. So this is something we'll talk more about later. Just for now, We'll talk about inheritance vectors and this 2n minus f, but for now, just remember that you need to check it in case it's too big for the computing facility you have. Again, you see there are 124. What's going on? Oh, look at this here. It tells you you have no marriage rings and you have no loops. The singletons are unconnected individuals. So that tells us that in this one where we had an extra constituent pedigree, it's not a singleton, it's a group that somehow is unconnected to the rest. Now, notice in this tells us that there are individuals with multiple mates. It tells us that in pedigree 1000 or whatever, it's that big number, 10,086, individual 3346 has two mates, 14 and 15, and so on. We'll talk a little bit more about that in a minute. There are possible problem pedigrees for S.A.G.E. And these are, for example, you may have a mating ring, okay? And this other one here, that's a loop, and the SIB pairs are, this is SIBs mating. You can see these two SIBs are mating, the pairs of SIBs. And on the right, there's a loop with consanguinity. On the left bottom, there's no consanguinity, but there is a loop. Now, for those of you who know anything about graph theory, these are called cycles, but geneticists always call them loops. And for all I know, it may be my fault. Maybe I called them the loops. I don't know. I don't know who called them loops first, but mathematically, they are cycles in the graph. So here's a loop with consanguinity. This pedigree has also a loop with consanguinity, and you can see the individuals involved. In the top left are 3 and 4, in the top right 7 and 8, and in the bottom left individuals 9 and 5, and on the bottom right there's a loop, consanguinity, and multiple mates. You can see individual 2 is married to 2 different women, or at least has children by 2 different women. So if you look at this, what this is telling you, the individual, the pedigree 1, individual 1 has multiple mates, has mates 4 and 2. Next line, individual pedigree 1, individual 2 has multiple mates 1 and 3, and so on. And if each ID in one of the mates columns also appears in the individual column, there may be a mating ring. And if we look down the bottom, we see in pedigree 3, the pair 10 and 9 are related individuals, and then similarly in pedigree 4, individuals 3 and 4 are related. This is telling us those pictures we just saw. Now let us talk about familial correlations. The correlation coefficient is it measures linear association. And the correlations calculated by F-core are consistent estimators of the true correlation if they're based on pedigrees randomly sampled from the population. Otherwise, they just reflect what is in the sample. They usually underestimate the they usually underestimate the population parameters if they are based on families ascertained via probands. Those, in other words, persons with extreme phenotypes. Note that we are not, these estimates are not maximum likelihood. There's no distributional assumptions at all. So correlations are the interclass if two classes of persons are involved, such as a parent and a child, or a grandparent and a grandchild. But they are intraclass if only one class of persons is involved. Now you've got to remember that's very, we'll come back to that in a minute. Consider degree of relationship. So the interclass ordered pairs could be parent offspring, grandparental, avuncular, great grandparental, great avuncular, half avuncular, and if the degree of relationship is infinite, then they're just marital or spouse. Those are the interclass correlations. The intraclass are unordered pairs, and we can think of self as being intraclass because there's only one class, if you like, and the first degree intraclass are siblings, second degree are half siblings, and third degree are cousins. Let me show you what I mean by those terms. This is a great avuncular pair. It's the sib of a grandparent. This next one is half avuncular, the half sib of a grandparent. Now, if you'll excuse me 1 minute. These are the main type correlations are classified into subtypes, and subtypes allow for the difference in sexes in the pedigree members. So if we look at the sibling type, we have 3 subtypes. We have the sister-sister, the brother-brother, and the brother-sister. The sister-sister and brother-brother are intraclass, while the brother-brother is the brother-sister is intraclass. Sorry, interclass. The Fisher explains that the intraclass correlation can be calculated as an interclass correlation from all ordered pairs. So if you have all your brother-sister pairs down in 2 columns, then you repeat it, say brother-sister first, then repeat it sister-brother, put all those down ordered, and then calculate the ordinary interclass correlation. That is one method of calculating the interclass correlation. Sorry, I've got all that mixed up. I'm talking about the what I'm talking about is when you have the interclass, yes, the intraclass. So when you have the intraclass, you have to look at ordered pairs. And Fisher explains how you can do that. And this is the way we do it. And so it's not maximum likelihood, it's just completely distribution free. So an F-core calculates main type correlations by pooling the subtypes. So it could pool all 3 sibling subtypes. It first of all calculates all the individual ones, the sister-sister, brother-brother, and brother-sister, and then pools them. Now there are 8 grandparental subtypes, and you can see them. We start on the left we see a grandmother and a granddaughter. It's a maternal, grandmother, granddaughter. Next, on this same picture, we see the maternal grandmother, grandson. And next we see again, now these are also grandmother, granddaughter, grandmother, grandson, but they're paternal because the intervening parent is male, and so on. Now, altogether, there are 2 to the power 3 or avuncular subtypes, and 2 to the 4 or 16 third-degree relative subtypes if the main type is interclass. However, well, in general, the number of subtypes for nth-degree relatives is 2 to the power n plus 1 if it's interclass. But if it's intraclass, it's going to be fewer. Look at this picture. These are first cousins. So every little picture, there are 16 little pictures here. And you look along the top row of white individuals, you see it's 2 females who are SIBs, then a male and a female who are 2 SIBs, then a female and a male that are 2 SIBs, and then 2 males. And if you look at the next row of white ones, it's exactly the same, that row. The third row of white ones is the same, and the fourth row is the same. Now look down the columns. First of all, you see in red, or well, pink, whatever that color is, mauve maybe, you have 2 daughters. Or these will be cousins. No, these are the offspring of the 2 SIBs. In the next one further down in this same column, you have a girl and a boy. And then you have a boy and a girl, and lastly a boy and a boy. And the next column is exactly the same. You have girl, 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 boy, boy, girl, boy, boy, and so on. They're all exactly the same. So there are 16 of these pictures, but notice some are really identical. Look at that equality sign at the top there. That is exactly the same. That is saying you have a SIB pair that are male and female, and they have 2 girls, and you see that's all it's saying, that equality, because you can just flip the one over and they're the same. Similarly, in the left-hand column, you can see those 2 middle ones are exactly the same, and in the center you see another pair or 2 pairs that are exactly the same. Altogether in this picture you have 6 equality signs. So what you have is a total of 16 minus 6, or 10 different subtypes. Now I want to talk about multiple variables. If one variable is involved, the correlations between relative pair types, that's just what the correlation is. But if there are 2 variables involved, we call the correlation a cross correlation. So this is our terminology here. If there's only 1 variable, it's just the ordinary correlation. If there's 2, it's a cross correlation. In the case of interclass cross correlations, we have 2 possibilities. We may correlate either X measured on a member of class I with Y measured on a member of class J, or conversely, X measured on a member of class J with Y measured on a member of class I. So how do we get their standard errors? So these are calculated using a second order Taylor series expansion. This is sometimes called the delta method, replacing all correlation parameters with their respective estimates. Now, unfortunately, this may require other non-estimable correlations. Give me a minute. So, as I said, we use the delta method, and the output also gives the standard error, which is the square root of the estimated variance. When other correlations, the point is that you may need other correlations. For example, in order to calculate the standard error or the variance of the SIB-SIB correlation, you need to know the parent-offspring correlation. Well, you may not have any parent-offspring correlations in your data and the parent-offspring pairs in your data. So when other correlations are needed, the program will indicate the smallest number of pairs needed for such a correlation. If there's only one pair or no pairs, that correlation is just not estimable. So if you don't like that, it's possible to suppress the calculation of standard error if it requires other correlations that are non-estimable in the sample data. But otherwise, it might just put them, it'll assume they're zero and it will put it in brackets so you can see it. For an intra-class correlation, there are two extreme possibilities for weighting the pair when the class contains more than one pair. Consider a SIB ship of size 3. There are 3 different pairs of SIBs. One extreme assumes the pairs are independent. The other assumes they are highly correlated. And this paper, Matthew et al., finds the best average of these two. And so for an intraclass correlation, we report this best average. What do I mean by best? Well, it's best in the sense that if you use this variance or standard error, which under this we report the standard error, the square root of the variance. This leads to a confidence interval with the appropriate coverage if you use Fisher's Z transformation of the correlation coefficient to get your interval. So that's what we mean by best. Okay. I think we've gone rather fast, so we're ready for questions. Everybody wants to take a break too fast. I've gone much faster than I meant to. What time are we supposed to be now? I've forgotten.
We are supposed to end the 11 o'clock, but we are about an hour early. But I can actually show the live PEDINFO because PEDINFO demonstration was not done live, but just in case we have time, I can show. Right. I mean, I was planning on showing the PEDINFO live if you would like to see.
Okay.
Or that we went through the slide.
Are you going to go back to those slides?
I mean.
Or no, it's up to you.
Let me stop share. And then now. I will show you actually from the beginning. Where did my Zoom control go? me show you what I am sharing to my window. Now you see my window right there. So I will actually start S.A.G.E. This is what you see when you start S.A.G.E. And then I will create a new project. I will designate the directory that where my project go. I want to put it right there. And then I want to give the name. Maybe it's like a live demo 1. And I am creating, actually, since we have the DBH data, I would like to use those S.A.G.E ready formats files. So I'm gonna click the third options right there. And then in here, now I have to add my parameter file and the data file. By default, I list 2. So I have my demo info file, and this is the one that we just showed you. So I have a couple of them that today I'm going to use the Schizophrenia and DBH demo parameters.
Can you make your picture bigger or not?
This one, I mean, this is by default this size. I will make it a little bit bigger. I just wanted to show the whole screen so that I can show you when the task window pops up, you can actually see it. If I just share this screen, the not whole screen, but just the S.A.G.E window, then you won't actually see the task window pops up. So that's why. But later on, I can make it the S.A.G.E to be just a bit bigger. Okay. So now I just added a parameter file, and now I am adding the data file, which is a Schizophrenia. Okay. And then next. Now it just confirms the finish it. And then you see this is like kind of small here. From here, you can actually make it little, like make this big S.A.G.E window to be like a smaller. And then, but what I wanted to share is actually, okay, move this one to this one. So how you start your PEDINFO job, just like I showed you through the slide, you just drag and drop PEDINFO on the right there. See, by default, it just automatically generates a parameter file. Now it says data file is missing, so I'm gonna just grab, drag, and drop it right there. So now it has the both parameter file and the pedigree file. So it also shows right there. So now either you click this or click next, which brings to your the analysis definition panel. And now you want to click to see which trait that you want to analyze. So we decide to do the affection status for the first example. Click the affection status. Okay, and now run right there. So this is the one that it was popping up to make sure these are the options that you choose, right? And then, okay, then see right there. This is the taskbar that I want you to see, that it just automatically comes up. Okay, and now it says finish it right there. So let's go see. Under here, now we only had previously input files only, right? But now you see the output file generated right there. Okay, and this, just double click this one, then it will automatically show this output file that we were just looking at it. Now, that's what I wanted to show you. Let me see, making this small. Now you see a little bigger of like an output file, right? Yeah, this is how you actually run your first PEDINFO job. Okay, and then if you wanna, let's see now, I think the second example, we actually, so now with the second example, we analyze the DBH data. So now, okay, I want to learn another PEDINFO. What you do is just to drag and drop PEDINFO to the job. It automatically pops up the second PEDINFO job. Okay, and it says parameter, data file is missing. So go to the data and drag your the pedigree file, drop it right there, okay? And then go to your analysis pane, analysis definition pane, and then in here, click DBH, okay? And I think in the second example, we actually wanted to have the calculations or like the per pedigree basis, right? So we want to click that and run. And then it now says this is the second option, each pedigree. Let me make it a little bit bigger so that it's easier to see. See? So second option now it is true. Okay. Okay. And it is running right away. As soon as it says okay. Now if you go to the second PEDINFO, we have outputs right there. And you see the DBH trait, the output file we were just looking at.
Now, Yunju, there's a, we have a request in the chat to show us the .inf files, the information files, see what they look like.
Okay, let me go back.
And of course, we should have looked at the information file first. That's always what you look at first, because there's no point in looking at the results if the information you put in is not good.
Right. Yeah. So this is the one that task, the pane that just automatically popped up. I wanted to show this one, so that's why I was making it a little bit bigger. Okay, close up the output file and then let's double click the information file. This is what it looks like in the information file for this one. Okay, the first part actually just gives you by default the first 10 rows of your paragraph file. Okay, so and then where your paragraph file was located. Okay, with the name of the paragraph file and where, and the first 10 rows. So it will be like the first 10 individual in your paragraph files. Okay, and then the next table, it's for the same people, same 10 people. It also gives you the trait and the phenotype value or any values that not the marker value, but any phenotype value, which is a trait or covariates. Okay, from your pedigree file that was specified in your parameter file. I will show you what it mean by that. You see, in your info file in here, this is the parameter file we used, right? So in parameter file, you have this many 1, 2, 3, 4, 5, 6, 7 different the trait that we specified, right? Which was read in from your pedigree files, okay? So in your INF file, the second table actually shows you those traits that was read in from your pedigree files, okay? But you will actually notice there is something that you didn't specify. One, the sex code, familial indicator, and founder indicator, and pedigree size. Those 4 phenotypes are actually automatically generated by S.A.G.E. So any sex code that you actually specify, like a male or female or 1 or 2, doesn't matter how you actually specified in your pedigree file, it will automatically generate like a 0, 1 indicator variable, so which is called like a sex code, sex underscore code. So that if you would like to use your sex code as like one of the covariate in your analysis, you can actually use this as if it is like one of the traits you have in your pedigree file. And also in here, familial indicator is just whether this is a member of the family or not. Okay, since we have like every individual was actually a member of family, it says it's a familiar. So it is a member of the family. And this will actually show founder indicators. Okay, if like this case, in this person, it says founder indicates 0, and the next person founder indicates 1. It's because if you look at this table, first the individual has the 2 parents, which means that this person is not a founder, so it will be 0. And then second individual, the 2 parents are missing, which means this second individual is a founder, so it will have a 1 there. That's what founder indicator is. And that the pedigree size is another variable, the phenotype variable that it is automatically computed inside is just giving the pedigree size. Like this first family, 1, 2, 3, 4, 5, 6 individuals are in this first pedigree. The pedigree and the family, I will just use interchangeably, which means the same name. Okay, so first 6 people will have 6 as a value for this pedigree size, and the second pedigree 1, 3, 3, 1. Even though we only see first 4 individuals, there are 14 individuals in that pedigree, so it will have like a 14 for the rest of the individual in this family. So, I mean, there is the parameter file. The parameter file, you can actually specify to print out everybody, not just the first 10 individuals. That's one of the options for like a verbose. By default, it is verbose equal 10. If you say verbose equal 100, it will just print out everybody, like up to 100 people. Okay, if you know that you have over like 2,000 people and says verbose equal 2,000, then it will print out everybody. Okay, so you can just change the number. Okay, and then as we saw from one of the PEDINFO output that Dr. Weston was explaining, there was like a 123 the pedigree, but there was 124 constituent subpedigree, right? Which means this is exactly what it means. Pedigree, the name 3082 has 2 constituent pedigrees which are disjoint from one another. So it will actually give you those kind of information in this INF file. Okay. So any other question you'd like to see in this demo?
That was very helpful, Yunju. But you should always remember that, especially if you are creating new variables and you want to make sure you've created it correctly, but you should always check the .inf file, always. It makes some, because if there are errors there, there's no point in looking at any results at all. Okay, so now it is.
Robert,
Yes.
Can I ask you to address a couple things?
Sure.
I know what the answer is, but this is for students. So if you would address these things. First, I want to emphasize to the students, absolutely listen to what Robert and Yunju say, check the INF files first, because one of the good things about those little printouts of the first 10 people is you can make sure right there that the program is reading your data correctly, that you haven't screwed something up when you made your data. So that's the first thing to check in every program that you run. And S.A.G.E gives you these great ways to check it. But it'll also, as you go along, if there are other errors, that's where it'll tell you about them. And you need to know before you look at the results. So you always look at that first. But Robert, what I'd like you to talk a few minutes about, you explained about loops, marriage loops, consanguinity, etc., and said these can cause problems in S.A.G.E. Would you expand a little bit on
Sure.
If I have a pedigree with a marriage loop, or if I have a pedigree with a consanguinity loop, what should I do next? So I'll shut up and let you talk.
Okay. So especially when you get to programs like segregation analysis or linkage analysis, unless we're just talking about pairs, If you're analyzing pairs, it doesn't matter. It just gets all pairs. But if you are doing these analyses that assume the whole pedigree structure, there is no way S.A.G.E can do that. So what you have to do is judiciously cut the loops. And the way to do that is to cut somewhere and to replicate the individual that you so if you replicate, you put an individual in twice. I'm trying to think, do we have a picture somewhere? I wonder if we can go to slide, where are we? Oh, I can't find it here. Here we go. Go to slide 21. All right, can we do that, Yunju? Is Yunju there? Oh, I think she's gone away. Well, if you can,
yes, I am here. I am here. I am sharing it right now.
Go to slide 21. Yeah.
Yes.
All right. So these pedigrees, they cannot go through segregation analysis or linkage analysis. If you're just looking at pairs, yes, it can pick out all pairs, no problem. But so for F-core, there would be no problem. But for segregation analysis, you have to somehow get rid of that loop. So look at the first pedigree 4, top left. What you might do is you have to somehow cut that loop, and you might want to, for example, put the bottom individual, the pink individual, as an offspring to 3 and as an offspring to 4. Similarly, on the next one on the right, you might want to put that pink offspring as an offspring to 7 and an offspring to 8 separately without a parent. However, the best place to cut is towards the top of the pedigree. And so in pedigree 4, you might want to cut right up there, and you might want to replicate, let's see, you put a cut there, and so 4 would be like a founder. And then on pedigree 5, you might want to cut so that that father of 8 is a founder. Okay, not a, it's difficult to say exactly what the best thing to do is, but you really want to cut as towards the top of the pedigree. Look at pedigree number 6. Pedigree number 6. There you might just want to, well, you could, for example, eliminate that pink consanguineous person at the bottom. You just lose some information, but the rest is all correct. And similarly on the pedigree 7, it's an art what to do, but you must make sure that when you go into programs that require the whole structure, there is no loop. And what you can do is you can run the program 2 or 3 different ways and check it doesn't make a material difference to the answer.
Right. Yeah. And one of the things that, sorry, I put my mic down. One of the things you and I've discussed many times is that if you pick the person you're going to make the cut at, if that person in a linkage analysis has been genotyped, then that's a good person for where you make the cut. Absolutely. As opposed to making the cut where there's an ungenotyped person. Of course, that's long forward from where we are now in linkage, but but this is where we're talking about pedigree structures. Yeah, thank you, Robert.
Right,
that
sure.
was helpful.
Yeah, it's really, I mean, there are, we have looked at but not implemented in S.A.G.E ways of doing this, and this was done specifically for non-human pedigrees. You look at dog pedigrees, cattle pedigrees, and so on. You often have many loops, and this is somewhere. The person who's done most work on that with me was Chris, what was his name? Strickland? I can't remember his name.
Yeah, I think that was his last name.
Strickland, yeah. So he has programs that will do all this, and you can look at, there's any paper by myself with Chris Strickland. Chris would probably be the first author. You can see all these details of what people can do and how it sort of works when you do this looping sort of stuff. It's interesting, but they don't occur so often in human pedigrees. They do occur, of course, but as I say, it's cutting where a genotype person has known genotype is much better than cutting where it's unknown, because it's known, then if you cut just above the known genotype, then you've basically still got all your information. Okay, so now it is, and I can't see this clock, it doesn't show its time on it. Oh, well. Well, I can't. So someone tell me the time, please.
Yeah, Dr. Aston, before we go, there is a question.
Are there more questions on chat?
Yes.
Oh, well.
The first one is, I think I can answer probably. In what situation would the familial indicator to be 0? That will be the kind of singleton case. Okay. And the sampling for pedigrees is done randomly. How do I know the minimum number of pedigrees required for a given study? Are there some guidelines or formula for sample size calculations?
Yeah, I think one of the best websites is the National Cancer Institute. And maybe, Joan, maybe you can tell me, there are websites for at least if you have unrelated individuals, what sample size do you know that, Joan, by any chance? Oh, she's off. Okay, but there are lots of.
No, I'm not off. It just took me a minute. Yeah, so sample size, it really depends on what the question is.
Of course.
And what kind of analysis are you talking about?
Right.
Yeah. Robert and I have done so many of these over the years. So if you're talking about familial correlations and segregation analysis, to have good estimates with small random error, with small error bars around them, you want a large number of families. So you're talking in the minimum 50s, really you'd like hundreds. Yeah. And for those values, which are trait based, to be valid and apply to the population, you want to ascertain them carefully. Robert will tell you a lot more about ascertainment when he gets to segregation. But even for correlation studies, you'd like to know that your sample of families is representative of the population, or if it's not going to be representative, you want to be very careful that you know what caused you to ascertain the families. Was it, as in the example, 2 cases of schizophrenia? So that's a subset of all cases with schizophrenia, but you could ask, what are the familial correlations in those kinds of aggregated families? So thinking about how you ascertained is important, but larger samples are needed there.
Yeah, let me say some. Oh, sorry, Joe.
Yeah, no, go.
Let me say something. I'm not sure if I've stated it yet or not, but you know, some people will get families because, you know, certain individuals are probans or what have you, or you have two people in the family who are affected, and then they will look at a correlation for a trait, let's say DBH, in those families. Well, now, and then what they find is they start getting negative correlations and they don't understand what's happening. Well, what you do have to understand is that the intraclass correlation, or in fact, any of these correlations, they assume that the mean value is the same for all classes. Okay. So for example, if you have parents and offspring, and they may differ by age, and I think we will talk a bit about that later on, but the point of what you might do, but the most important thing to realize is you must make sure the means of the two classes are the same and the variances of the two classes are the same. If they're not, then you'll get meaningless results. Remember, when you calculate the intra-class correlation, you basically put everything down twice, one order then the other order. And so you are assuming that the classes have the same means and variances. And a good thing to do is to maybe standardize them before you start. And I can't remember whether it's today or it wasn't yesterday, I don't think, last time, but we will talk about that. You must make sure for these correlations that the classes all, for especially the intra-class correlation or the inter-class correlation, that the classes have the same means. Absolutely essential.
Yeah,
okay.
Yeah, that's really critical. If you have a trait with a cohort effect where, you know, it's been changing over time because the environment's changed or whatever. Yeah, so understanding your trait is really important.
Absolutely, yeah. Absolutely.
And you know, we were talking about sample size. So for linkage, there are multiple programs out there to help you estimate sample size, just like there are for association studies. So there are lots of programs to do it, but one of the things Robert pounded into me when I was his student is you have to understand that in any power calculation, you are making assumptions.
Absolutely.
And if those assumptions are valid, then you get a good estimate of your power. But if those assumptions are wrong, your power is not good. So like for linkage, if you assume that your trait is autosomal dominant and 100% penetrant and very rare, and that everybody who has this trait has it because of one gene, and you do your power calculation, it'll tell you how many families you need. Well, let's assume you got everything right, except for the fact that there are 5 different genes that cause this in different families, right? Like breast cancer and BRCA1, BRCA2, CHEK2, etc. So you can have a whole bunch of highly aggregated families that look autosomal dominant and look really highly penetrant. But if there's 5 different genes, a different gene in each family, the power calculation you did is wrong. You've got maybe, if you're lucky, about a fifth of the power you thought you had.
Yeah, there are, and the other thing I would like to say, that, you know, everything we do, even when it's maximum likelihood, is really asymptotic. And if you don't have large samples, just get out of genetics, okay? Just get out. you just, there's no point in doing anything with small samples. There just is no point at all.
Right. And you know, for linkage studies, it's kind of two different ways to get big samples. You can say, I have a lot of small families, or I have maybe only one big family.
Exactly.
With a lot of information. So it always comes down to information content.
Yep.
And that is another thing I learned from you, Robert.
We shall see this. I think it's in not today, but I think we'll see this on Thursday, I think. Yeah. Okay, well, thank you, Joan. Thank you so much for helping me. I'm getting old and forgetful, and you're
no, you're not. But this was the best thing. I know you and Drew, you think the same thing. This is the best thing of working with Robert, is we get these great conversations and we all learn so much.
Oh. Well, now, what time is it now? Can we?
It's 11. Excuse me. It's 11:43, and I guess we can take a break now, and then come back at like 11:10, because the first break is like 11 to 11:10. We are about 10 minutes early.
All right.
Early,
so let's come back at 11:10. Yep.
Okay.
And I need my break. Thank you. We'll
Okay.
see you all at 11:10.
Thank
Okay.
you. See you on 11:10.